Okay, in our last discussion, we have seen two CPU scheduling algorithms. One we have seen as FCFS, or first come first served scheduling algorithm, and the second scheduling algorithm that we have seen is shortest job first, that is SJF scheduling algorithm. And we have also seen that if we use shortest job first, instead of the first come first serve type of scheduling, then the average waiting time is reduced. So today we'll discuss about other CPU scheduling algorithms. Now before starting other scheduling algorithms, let us see what is meant by a process state diagram. So to discuss about process state diagram, you will see that most of the programs or most of the processes, as we have said, that a process is nothing but a program in execution. So most of the processes, they possess a typical characteristics. That is, when you run a program, the program does not take CPU time for the entire duration. It is executed on the CPU for a part of the time, then it waits for some IO operation. The IO operation, maybe it is waiting for some input from some user, from the user, or maybe it is waiting to read a file from the disk, or maybe it is waiting to get some input from some device. Okay. Similarly, while execution, it is also possible that in between it keeps on giving some intermediate output to some output device or some intermediate output to the user. Okay. So all these operations, whenever the program tries to access any of the IO device, we'll call this as IO burst of the program. And the duration for which the program is actually executed on the CPU, that we will call as CPU burst of the program. Okay. So this is the characteristics which is exhibited by almost all the programs. So the characteristics will be something like this. For a duration of the time it is actually executed on the CPU. Okay. For next duration, next few time interval, it will perform some IO operation. Next, again it will perform CPU operation, then again some IO operation, then again some CPU operation, and it will continue like this, and then finally there will be a final CPU burst and the job will be terminated. Okay. So all these green intervals, let us call them as CPU burst. Okay. And all the red intervals, let us call them as IO burst, because this is the time during which the program is performing some IO operation. Okay. So almost all the programs, they consist of a number of alternate CPU and IO bursts. Of course, the first one has to be a CPU burst when the program is initiated, and the last one has to be also a CPU burst when the program is terminated. In between, we have a sequence of CPU and IO bursts. Okay. So a process state diagram can be formed like this. Whenever any user submits a program for execution, but maybe the CPU has not yet accepted it. Okay. So we have said in the last class that the CPU can execute a program or the CPU can access any data only when the program or the data resides in the main memory. As long as it is on the hard disk or on any secondary storage, it cannot be accessed by the CPU. Okay. So whenever an user initiates a program, firstly the program has to wait for getting some space in the main memory. Only when it is loaded into the main memory, that is a job which is to be done by the loader. So only when it is loaded in the main memory, then only the program can be executed by the CPU. Okay. So first, when you start execution of a program, if you are working on Unix based system, you know that after compilation of a program, you get an executable file which is called a.out. Okay. Now, if I want to execute that program, I have to give a command a.out. Okay. But that does not mean that the moment I give the command a.out, the program starts execution immediately. Firstly, the executable code, maybe the entire code or part of it that we'll see later, has to be loaded into main memory. For that, there has to be some space in the main memory. Only when it is loaded in the main memory, then only it is ready for execution. That is, the CPU can take that program and execute it. Okay. So when you initiate a program for execution, that is called a new job. Or the process enters a state which is called a new state. Okay. Then from the new state, when the program is loaded in the main memory and it is ready for execution, then we say that the process enters into a ready state. So this just says that the process is now ready for execution, but it does not say that it is being executed by the CPU. Only thing is, the process has moved from new state to ready state. Okay. Now, once it is in the ready state, then the CPU scheduler has to take the jobs, has to check all the jobs which are in the ready state, select one of them and pass that to the CPU for execution. Okay. So, a job can be executed by the CPU only when it is in the ready state. A job cannot be executed by the CPU when it is in the new state. Okay. So from the ready state, when the CPU actually executes the job, we call that job to be in active state. So the job becomes active from ready. Okay. And finally, when the job is complete, that is, all the CPU bursts of the job is complete, and even the last CPU burst for terminating the job, that is also complete, then the job comes out of the system, and the corresponding state we call as halted state. Or you can also call it finished state. Okay. Usually the term which is used is halted. So from active state, the job moves to halted state when the job is complete. Okay. So this may be completed naturally, or maybe if there is some abnormality in the job, in which case the CPU will terminate the job forcibly. Then also the job comes out of the system and it enters into halted state. Okay. So from new state, it moves to the ready state. From ready state, it moves to active state. From active state, it moves to halted state. Now, while the job is in active state, that means it is being actually executed by the CPU. That means the job is passing through one of its CPU bursts. Okay. So as we have seen here, that the job consists of alternative sequence of CPU burst and IO burst. So at the end of a particular CPU burst, when the job is active, then maybe it is willing to perform some IO operation. Now, when an IO operation is to be performed, then the job does not have anything to do with the CPU. The CPU need not be busy or need not wait until and unless the job is complete. Okay. So what you can do is, whenever the job wants to perform some IO operation, you just remove it from the CPU, push it into another state which is called an waiting state. That is, it is waiting for some IO operation. So you call this as an waiting state. So from active state, the job or the process moves into an waiting state when the CPU is released. This CPU is free. Now, this time of the CPU can be utilized for execution of CPU burst of another job. Okay. Now, when this waiting state of the job is complete, that is IO operation, which the job needs, that is complete, what you do is you move the job from, there is two ways. Either we can move the job from waiting state to active state, but in that case, we have a risk that maybe the CPU burst of another job which was in progress, that is not yet complete. So if that is not yet complete, I cannot move this waiting job to active state immediately. So what we do is, from the waiting state, you move the job to the ready state. Okay, that means it is again in the ready queue. The job becomes ready, and again the CPU scheduler later on decide that when to give this job to the CPU for execution of the next CPU burst. Okay. So you find that from the active state, the job will go to waiting state, from waiting state to ready state, then ready state, from ready state it will again be active at some later time. Okay. So any typical job will go through a number of cycles from ready state to active state to waiting state to ready state again. Okay. So it goes to a number of cycles in these three states, and then finally when the last CPU burst of the job is complete, it will come out of the system and it goes to the halted state. Okay. Now this is where the multi-processing capability of the machine comes. If I have strictly a single processing machine like the earlier DOS-based personal computers, okay, where you know that you could execute only one program at a time. You cannot execute more than one program at a time in the DOS-based system. But there again, the programs will have similar nature. It will consist of a number of CPU burst and IO burst, which will come one after another. But in such cases, whenever a CPU burst is executed, whenever an IO burst is executed, the CPU remains idle. The CPU does not perform anything. That means you are wasting the CPU time, which you can avoid following this kind of state diagram. That is, when one job wants to perform some IO operation, you use the CPU for execution of the CPU burst of another job. Okay. So effectively, as if we are executing more than one jobs simultaneously on the same machine, or we have a multi-user or multi-processing system. Of course, multi-processing does not mean that you have to have more than one processor or more than one CPU in the computer. Okay. And we also just mentioned in the last class that when I say that more than one jobs, more than one programs can be executed simultaneously, it is not strictly simultaneous. You find that here, following the state diagram, I can execute more than one jobs in time multiplexed fashion. They are not strictly simultaneous because one CPU cannot execute more than one instruction at the same duration of time. Only we can execute in a multiplexed fashion. So here again, the multiplexing is in the form of CPU burst and IO burst. When you execute CPU burst of one program, other program is actually performing the IO burst. Okay. So having this in this multiplexed fashion, I can have a multi-processing system even if I have a single CPU in the computer. And this is what is known as the state diagram of a process. Okay. Now coming back to our CPU scheduling algorithms, as we said that the responsibility of the CPU scheduling algorithm is to take a job from the ready queue, that is, it has to select a job from all those jobs which are in the main memory. So it has to take a job from the ready queue and allocate that job to the CPU for execution. Okay. So obviously the jobs which are there in the ready queue, they are waiting in the queue for execution of their next CPU burst, isn't it? They are just waiting for execution of their next CPU burst. We don't know what will happen after execution of the next CPU burst. Maybe the job will be terminated and it will go to halted state, or maybe after completion of the next CPU burst, it will perform another IO operation and it will go to waiting state, or this is also called IO waiting state. That is, it is waiting for some IO operation to be complete. Okay. So one of the responsibilities, I mean the major responsibility of the CPU scheduler is to get a job from the ready queue, give it to the CPU for execution of the next CPU burst. Okay. So all these two CPU scheduling algorithms that we have said, that is whether it is first come first serve or whether it is shortest job first, this time duration that we have specified, that is for J1 15 time units, for J2 8 time units, J3 10 time units, or J4 3 time units, these time units are actually the execution time of the next CPU burst. Okay. So in order to have an efficient scheduling algorithm, we have to have some idea of what is the next CPU burst time of the job. In case of first come first serve, I don't have any such problem, because here my only criteria is the job which has arrived in the ready queue first, that has to be executed first, without bothering about what is the next CPU time of that job. But in case of shortest job first, that is the SJF scheduling algorithm, because we are executing that job first for which the next CPU burst time is minimum, and the job which takes maximum CPU burst time, that is to be executed last. So we must have some idea about what will be the next CPU burst duration. Only then we can perform this task, the scheduling using shortest job first. But it is never possible to know exactly that what will be the time required for the next CPU burst. Okay. So we have to go for some prediction of the next CPU burst time. And for that, you use a predictor, and the predictor is of this form. For shortest job first, that is tau n plus 1 is equal to alpha times Tn plus 1 minus alpha times tau n. Okay. Where tau n plus 1 is the predicted CPU burst time of the n plus first CPU burst. Okay. Tn is the exact nth CPU burst duration, and tau n is the predicted nth burst duration. Okay. So find that for prediction of that next CPU burst time, that is tau n plus 1, we are making use of the actual nth CPU burst time, that is the previous CPU burst time, and the predicted nth CPU burst time. Okay. And we are taking an weighted sum of these two, where Tn tells you what is the immediate past of the job, and tau n gives you some indication about the history of the job, because tau n is accumulated. So this gives you some history of the job, and this gives you the immediate nature of the job. You take an weighted average of these two to give you what is the next CPU burst or predicted next CPU burst of the job. Okay. So once we can predict this, I can use this predicted value, the predicted CPU burst duration, to be used by the SJF algorithm. Okay. Now the question is, how do you get the first CPU burst duration? That is tau 0. Okay. Because till that time the job has not been executed for any of the CPU burst, so I don't have any any past history of the job. Okay. So that is why usually what can be done is, for the first CPU burst, you execute the job in first come first serve basis. Okay. So once you execute the job for the first time, I know what is T1, that is the first CPU burst. Okay. weight that by alpha and 1 minus alpha times, now I have to know what is tau 1, but tau 1 I don't know, because this is the first CPU burst which is T1. So, tau 1 is unknown, and using this what I am doing is I am predicting the second CPU burst duration of the job. So, I am predicting tau 2 from T1 and tau 1, of which I know T1 because first time the job is to be executed in first come first serve basis. Okay. So, one of the two things can be done to replace this tau 1. I can assume tau 1 to be same as T1, as if the past history of the job is same as the immediate past nature of the job. So, I can assume tau 1 to be equal to T1, or I can even put tau 1 equal to 0. Okay. So, using any of these two, I can predict what is T1, and based on this predicted T1, I can predict what is tau 2, and based on this predicted tau 2, the job will be scheduled for the next CPU burst. Okay. Now, find that this parameter alpha tells you that how much weightage you want to give on the immediate past and how much weightage you want to give on the past history. Okay. So, if alpha equal to 1, then always your predicted next CPU burst time is same as the immediate past CPU burst time. So, if my previous CPU burst time was say 4 milliseconds, I assume that the next CPU burst time will also be 4 milliseconds. On the other hand, if I set alpha equal to 0, in that case tau n plus 1 becomes equal to tau n. That is, if the previous predicted time was 4 milliseconds, I assume that the next CPU burst time will also be 4 milliseconds. So, these are the two extreme cases when alpha equal to 1 or alpha equal to 0. So, usual practice is you choose a value of alpha between 0 to 1, so that you can have a proper mix of immediate past and past history of the job. Okay. So, your SJF or shortest job first scheduling algorithm has to schedule depending upon this predicted time, because I do not know exactly what will be the next CPU burst time. Okay. So, some such prediction can be used. Okay. Whereas, in case of first come first serve type of scheduling, we do not need any prediction, because there the CPU burst time does not come into picture at all. It is only the order of arrival which is important. Okay. Now, another CPU scheduling or process scheduling that can be used is what is called a priority schedule. What is this priority scheduling? In case of priority scheduling, you can specify the priority of a job. Okay, I can set the priority levels of different jobs, and in that case, I want that a job which is having the highest priority should be executed first, and the job which is having the lowest priority, that should be executed first. Okay. So, this is similar to what we have done in case of shortest job first scheduling, that a job which is having the smallest CPU burst time, that is to be executed first. In case of priority scheduling, a job which has been specified to be highest priority, that is to be executed first. Okay. Now, if you compare this priority scheduling with shortest job first scheduling, you will find that SJF is nothing but a special case of priority scheduling, because there I can say that the priority of a job, say Pi, priority of ith job, is nothing but the reciprocal of tau n plus 1 I, where tau n plus 1 is the predicted next CPU burst duration. Okay. So, in case of shortest job first, since we are executing the job having the minimum CPU burst time first, so it is just the reciprocal of that which tells you what is the priority of that job. So, I can also say that the shortest job first scheduling technique is nothing but a special case of priority scheduling technique, where priority is nothing but the reciprocal of the next CPU burst duration. Okay, so this is one case. In other case, the user or the system administrator can set the priority of different jobs, and depending upon that priority level, a job which is having maximum priority or highest priority, that will be executed first. A job which will have the lowest priority, that will be executed last. Okay. Now, these three kinds of CPU scheduling techniques, that is, the first is first come first served CPU scheduling, FCFS, or shortest job first scheduling technique, SJF, or priority scheduling. In these scheduling techniques, you must have noticed one thing, that we have assumed that once a job is given to the CPU for execution of its next CPU burst, the CPU cannot be freed or CPU cannot be taken out of that job until and unless that particular CPU burst is complete. That means our assumption is once a job is given to the CPU for execution of a CPU burst, that current CPU burst must be complete before allocating the CPU to the CPU burst of any other job.
So can we call SGF as priority scheduling?
Yeah, that is what I said. SJF, shortest job first, we are calling as a special case of priority scheduling, where the priority is defined like this. Okay, here the priority of job I is the reciprocal of the predicted next CPU burst time of job I. So, job whose predicted next CPU burst is minimum, that will have maximum priority, because we are taking the reciprocal of that as priority of that. Okay. So, for these three scheduling techniques, you see that once a job is allocated to a CPU, is given to the CPU for execution of a CPU burst, the CPU cannot be taken out of that job until and unless that entire CPU burst is complete. That means the job cannot be preempted. It has to come out of the CPU naturally at the end of the current CPU burst. Okay. So, these kinds of CPU, these three CPU scheduling techniques are normally known as non-preemptive scheduling. Okay. So, these are non-preemptive CPU scheduling techniques. We can have, as we have the non-preemptive CPU scheduling, we can also have the reverse, that is preemptive CPU scheduling. Now, what is this preemptive CPU scheduling? I can allocate a job to the CPU for execution of a particular CPU burst. But before completion of the CPU burst, if some situation arises when that job has to be stopped and the CPU has to be given to some other job for execution, then I should allow that. That is, the job can be preempted before its natural completion. So, that is what is called preemptive CPU scheduling. Now, if you study these three, you find that out of this first come first serve, as the name suggests, this should not be preemptive, because Here I don't have any other priority or anything. The priority is time of arrival. That means the job which has arrived first, that has to be executed first. The job which has arrived next, that has to be executed next. So naturally, this first come first serve type of CPU scheduling cannot be preemptive CPU scheduling. Whereas the other two, the shortest job first and priority scheduling, these two can be modified to get preemptive CPU scheduling. Okay, so how that can be done? Let us take an example. Say I have jobs J1, J2, J3, J4. Okay. Suppose the next CPU burst time of job J1 is something like, as we have done previously, so 15 time units. For job J2, it can be say 9 time units. For job 3, it can be say 3 time units. For job J4, it can be, let us put any value, so 5 time units. Okay. Now suppose we are going for this shortest job first kind of CPU scheduling. Now let us see how this will work. And we want to modify this CPU scheduling to make it a preemptive CPU scheduling. Okay. Now initially I have these jobs in the ready queue with this CPU burst times. Following SJF technique, the job which has to be given to the CPU for the first time is job J3, that is job J3 will start execution. Okay, and it has to be executed for 3 time units. Now I can have a situation that after job J3 has been executed for 1 time unit, for 1 time unit the job J3 has been completed. So what is the time left for this CPU burst? That is 2 time units. But at that instant of time, suppose another job arrives in the ready queue, say job J5, whose CPU time requirement may be 1 time unit. Okay, I'm working on shortest job first type of scheduling. Okay, now at this point for job 3, the remaining time is 2 time units, whereas in the ready queue I have another job whose time requirement is only 1 time unit. So again, following that shortest job first CPU scheduling, I should execute this job J5. Okay. So what I have to do is I have to terminate this job J3 here and start execution of job J5, and job J5 will be executed for 2 time units. Sorry, 1 time unit, because its requirement is 1 time unit. Okay, and the remaining time of job J3 is 2 time units. So after completion of job J5, so J3 is executed here, J5 is executed here. Okay, after completion of job J5, I have within the ready queue job J3 with remaining time of 2 time units. Other jobs have not been executed at all, so for them the remaining time unit remains the same. Okay, so at this point when job J5 is complete, again I have to check the ready queue, find out a job with minimum time requirement. So here you find that it is again job J3 which requires 2 time units. Okay, so I will allocate job J3 for execution, and when it will be executed for remaining 2 time units of the CPU burst. Okay. Now in between, if there is no other job which comes in the ready queue, arrives in the ready queue, after completion of job J3, I have to check the ready queue. And now within the ready queue, I have job J4, which requires 5 time units. So at the end of J3, job J4 will be given to the CPU for execution, and it will be executed for 5 time units, assuming that no other jobs arrive in the ready queue. Okay. So how we have modified this SJF technique? every time a new job arrives in the ready queue, I am checking what is the time left of the job which is being currently executed on the CPU, and what is the CPU burst time requirement of the newly arrived job. If I find that the remaining time of the current job is more than the time requirement of the newly arrived job, I will preempt the current job, okay, and give this next job, the newly arrived job, to the CPU for execution. Okay, so that is how we have modified this SJF technique, and now because we are allocating the job with shortest remaining time to the CPU for execution first, so we will rename this SJF as shortest remaining time first CPU scheduling algorithm, that is SRT CPU scheduling algorithm, or shortest remaining time first CPU scheduling algorithm. Okay. So following the same logic, the priority scheduling technique can also be modified to make it preemptive. So see, a job which is currently in active state, that will have some priority level. Now while that is in the active state, if any other jobs arrive in the ready queue with a priority higher than that, then we have to preempt the job which is currently active and give this higher priority job to the CPU for execution. Okay. Now if you do this, then there is a danger. That is, I have given a job to the CPU for execution which is currently of highest priority. Okay. And here the situation is dynamic. Every time a new job arrives in the queue, I am checking the priority of that job with the priority of the currently active job. So every time, whenever a new job arrives in the queue, if I always find that the priority of that job is greater than some job already in the ready queue, that means the job which is there in the ready queue with a lower priority, that will never be executed. Okay, it will starve for CPU time. That is again an undesirable situation. I do not want that any job which is given to the submitted to the machine for execution should starve for the CPU. So even after few years, that job does not get the CPU time to be executed. So you have to take care of it. So that can be taken care by a concept which is called aging. Now what is this aging? While the job remains in the CPU queue, in the ready queue, at regular intervals of time, you go on incrementing the priority level of the job. Okay, that means the priority of the job, now it is not only decided by the user or the administrator, the priority of the job will also be decided by the duration for which it is remaining in the ready queue. Okay, so because at regular intervals of time, you are incrementing the priority of the job, so there will be some time when the job will reach the maximum priority level, and when it reaches the maximum priority level, it will be executed by the CPU. So this is one way in which the starvation problem can be solved. Okay. Now coming back to our previous state diagram, you find that now this state diagram has to be modified.
The times is again to be done by the CPU itself.
Which one?
The calculation of all these priorities and all that.
Yeah.
It is to be done again by the CPU.
When I go for this shortest job first, the calculation has to be done by the CPU. So one point I didn't mention, that this CPU scheduling technique has to be very, very efficient, because the CPU scheduling technique works with the CPU burst. It should not so happen that to allocate a job having CPU burst time of 5 milliseconds, the CPU takes 6 seconds to decide that a job of 5 milliseconds has to be executed by the CPU. It should not be so, because in that case, most of the time the CPU will be wasting for decision making. This time is not available to the user. Okay. So the CPU scheduling has to be very, very efficient. I cannot have a much complicated algorithm to implement the CPU scheduling. Okay. So the time taken by the CPU scheduler, because that is also a software to be executed on the CPU. So time taken by the CPU scheduler program has to be negligible compared to the CPU burst time of the jobs. Okay. And that is very important. Right. Yeah. So as I was saying, that when I have drawn this process state diagram, we have said that the process can move from the ready state to active state to waiting state when the process is performing some IO operation. Then at the completion of IO operation, the process goes to ready state. Okay. Now, after talking about this preemptive scheduling algorithm, you find that the process can move to ready state from active state not only via this path. It is also possible that the process can move to ready state from active state directly because of preemption, isn't it? Because a job requiring a CPU burst time of say 5 milliseconds has been executed for 1 millisecond. After that, the job has been preempted. That means it needs another 4 milliseconds of CPU burst of CPU time for completion of its CPU burst. So even for that much remaining CPU burst time, it has to be in the ready queue. Okay. So I have to have another path to send a job from active state to ready state. Okay. So this completes the process state diagram. Okay. Now again, with respect to this process state diagram, you find that in a system, if I have all the jobs which require more amount of CPU burst, or the CPU burst duration is more, such kinds of jobs are called CPU bound jobs. That means they use more of CPU time and use less of IO time. There can be another kind of job which uses more of IO time and less of CPU time. That means the IO burst duration will be long and the CPU burst durations will be very short. That is, the job will be for most of the time in the IO waiting queue. Okay. And these kinds of jobs are known as IO bound jobs. So I can have two kinds of jobs. One is CPU bound job, where the jobs require more of CPU time. I can have another kind of jobs which are known as IO bound jobs, where the job require more of IO time. Now, if in a system, say in the ready queue, I have all the jobs which are CPU bound, I can have a situation like this. In the ready queue, I have all the jobs, I have the jobs, all of them are CPU bound jobs. That means for none of the jobs, IO operation is more, IO operation is very, very small, whereas CPU requirement is very, very high. So in such cases, you will find that the CPU time taken by the jobs will be quite high, whereas the IO devices will remain mostly inactive, mostly idle. Okay. On the other hand, if all the jobs in the ready queue are IO bound jobs, you will find that the IO devices will always remain busy, whereas there will be time when the CPU will remain idle. Okay. None of these are desirable, because we want that in a system, all the systems should be busy most of the time. That means they should be, the use of the system resources should be properly balanced. And that can be done only when in the ready queue I have a proper mix of CPU bound jobs and IO bound jobs. Okay. So there are two kind of schedulers that come into picture. One is, once the job becomes ready, then there has to be some scheduler. Once a job becomes new, then there has to be some scheduler which picks up a job from the new queue and puts that into main memory. That is, shifts a number of jobs from the new queue to ready queue. So there is one scheduler which performs that task. There is another scheduler which puts a job from the ready queue to active state. Okay, and as we have said, that the job which scheduler which puts a job from the ready queue to the active state, that is concerned, that is more concerned about the CPU burst time of the job. And the CPU burst time being very short, this scheduler cannot take much time to decide which job has to be made active. Okay, so this scheduler which puts a job from ready queue to active state is called a short term scheduler. Okay. The other scheduler which puts the job from new queue to ready queue, this is called a long term scheduler. Okay. So in a system, I can have two kinds of schedulers. One is a short term scheduler which decides that which job has to be given to the CPU for execution, and I have a long term scheduler which decides that which jobs, what are the jobs which should reside in the main memory. That means what are the jobs which should be there in the ready queue. Okay. Now, as I said that in the ready queue, I don't want that all the jobs should be CPU bound or all the jobs should be IO bound, because in that case, one of the resources will become idle. Okay. So in the ready queue, I should have a proper mixture of the CPU bound jobs and IO bound jobs. And that will be the responsibility of this long term scheduler to decide that if there are many jobs in the new queue, there are many jobs which are in the new state. Out of those jobs, what are the jobs which should be pushed into ready state? Okay. And you find that the duration of this long term scheduler decision is quite long, because a job will move from ready to active to waiting to ready or ready to active to ready. This cycle will continue for a long time. That is the entire lifetime of the job. Whereas the scope of short term scheduler is very short. This only remains for a particular CPU burst time. So I can afford to have a long term scheduler which is very, very complicated with respect to short term scheduler, because now long term scheduler can take more time to decide that which job should be pushed into ready state from the new state. But short term scheduler cannot take long time to decide that which job has to be made active from the ready state. Okay. So that will be the responsibility of these two kinds of schedulers. Okay. So with this, we complete today's discussion. Next day, we'll continue with other CPU scheduling techniques.